Hello everyone. In this video, I'm going to show you on how to represent binary number with its floating point single using single precision floating point binary number representation and double precision floating point binary number representation. So, let us first discuss this single precision floating point binary number representation. So in this case, what we are going to convert, I have this given here, which is 1001111, which is a binary number with floating point. And for us to convert that or to represent that using single precision format, I'm going to discuss first how does single precision format looks like. So single precision format looks uh, like this. Uh, it is consisted of three parts, which is the sign bit, the exponent, and the mantissa. So first, a sign bit is consist of a sign bit have a single bit, which is 0 is positive, and the exponent have 8 bits for the single precision floating point. So it will become like this, like that. And for the mantissa, Mantissa is consisted of 23 bits. So in short, it will look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Just like that. So a single precision floating point representation will look like this. So in short, this one or this binary number with floating point will soon be looking like this when we convert it. So without further ado, let's try on converting it. So again, mantissa is consisted of 23 bits, exponent is consisted of 8 bits, and sign bit is consisted of 1 bit. So for us to represent this using single precision format, what we are going to do first is we are going to move this point to the left, and when we move the point, we should make sure that there is a number or a bit before the point, a single number, a single bit. So it will look like this. So 1001101. So now that we move the point to this part to the left, it will now become like this. And we should always count how many times did we mhm, did we move the point to the left. In this case, we move 1, 2, 3, 4, 5 times. So we move 5 times, so that will be 2 to the power of 5. So after that, what we are going to do next is focus on these decimal points. Then use that, which is 0011, and now that we have this, we will use this to get our mantissa, which is the 23 bits. And since this is 2, 4, 6, 7 bits only, we will substitute a multiple of 0 to get a 23 bits. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21, 22, 23. So our mantissa will look like this, just like that. So that will be our mantissa. And how about for our exponent? By the way, our sign bit will be 0 since we have a positive number here. For the sign bit, what we are going to do is we just use this 5, the number of times you move the point, and add it to the bias of the single precision format, which is always equal to 127. So the bias is lock or always be equal to 127 for the single precision format. So after that, we just add them. So that will be equal to 132. And what we are going to do next is, since this is a decimal point, this is a decimal one, we are going to convert that into its binary. So to convert that into its binary, I'm going to use this table here. And I'm going to find numbers from this row, which when I will add them up will be equal to 132. So in this case, I'm going to use 128 and 4, since that is equal to 132 perfectly. And what I'm going to do next is just add 0 to the blank spaces, like that. And this will now be our exponent. So that is 100000100. So now we have our single precision representation of this one. So the single precision floating point binary number representation of this binary number is this. And how about for its double precision floating point binary number? Um, they have the same steps to follow up to here, but what we are but when we reach in this point where we use the decimal points, is that our mantissa for the double precision format will be consisted of 54 54 bits instead of 23 bits. So in short, we are going to substitute a lot of zeros to make these 7 bits into the 54 bits. So let me just do that. That's 7, 8, 9, 10, 11, 12, 13, 18, 19, 20. So that is our mantissa for the double precision representation. And for the exponent, what we are going to do in the exponent is, since the bias of the single precision floating point is 127, the bias of the double precision representation is 1023. That won't change. That will always be 1023. So when we add them up, we will get 1028. So, see, by the way, the exponent of the double precision representation is consisted of 11 bits. Since it is consisted of 11 bits, and this table is only good for 8 bits, we need to add two more what do you call this? Two more table or column. Let me just copy them. Let me just do this. By the way, sa 8, 9, 10, and 11, so you only need these three. So on, we need to just delete them. And we just need this 3 one here as our continuation. And for that, we will have here 8, 9, and 10. So how to get their value is just easy. Multiply 128 to 2 again. So it will result to 256. Then 256 multiplied by 2 will be 512. Let me just get it. 256 times 2 equal to 512. Correct. 128 times 56. So for the 2 to the power of 10, which is 512 times 2, well, 1024. So the same way of on how we converted the decimal earlier, we are just going to need to find values that when we add them up will equal to 1028, since that is what we are trying to convert. So this will now change. So for us to get 1028, we will use this 1024 and this 4 here. Get the exact amount of 1028. 1024 plus 4 is 1028. So again, put zeros on the blank spaces, and this value from here to here will be our exponent, which is 100. Wait, sorry for that. Which is why is this like this? Oops. 100 and 00 So this will now be our exponent, which should be consisted of 11 bits. Again, for the double precision representation, instead of 23 bits for its mantissa, it will become now to 54 bits. And while the exponent, which is 8 bits on this single precision, will now become 11 bits in the double precision. And for the sign bit, they always have the same one, which is only a single bit. So that is how you represent binary with its floating point using single precision format and double precision format. So thank you so much guys for watching and have a good day. Bye.